First of all, we can understand the size of Bhumandala by comparing it with the orbit of Uranus. Measured in yojanas, Bhumandala is slightly bigger in diameter than the orbit of this planet. Within Bhumandala, a ring-shaped mountain called Loka Loka is defined by the Bhagavatam as the outer limit of the luminaries. Perhaps coincidentally, this ring is about the size of the orbit of Saturn, the outermost of the planets visible to the naked eye. We can understand the scale of Bhumandala by comparing it with the Earth, the solar system, out to Saturn and Uranus, and the Milky Way galaxy. Bhumandala closely matches the solar system, but it differs radically in size from the Earth and the galaxy. If we compare the rings of Bhumandala with the orbits of the 5 planets, Mercury through Saturn, we find further alignments which give weight to the hypothesis that Bhumandala was designed as a map of the solar system. To show this accurately, we have to look at a geocentric model of the solar system. Here is the geocentric system as given by the famous astronomer Tycho Brahe. Note that Brahe has the 5 traditional planets orbiting the Sun and the Sun orbiting the Earth. In the 19th century, the South Indian scholar Tiruvenkata Ramanuja Geoswami compared the solar system with Bhumandala. Here is a diagram of his model. Tiruvenkata's model exactly matches the geocentric model of Tycho Brahe. In fact, this is the natural way to compare Bhumandala with the planetary orbits. Planetary orbit can be portrayed from a sun-centered or Earth-centered standpoint. Here we see how the orbit of Venus changes when we shift the camera's viewpoint from the Sun to the Earth. The sun-centered viewpoint is essential for modern orbital calculations, but the Earth-centered viewpoint is necessary for all Earth-based observations. In a geocentric model, a planet orbits the Sun, while the Sun orbits the Earth. This produces a looping motion like that produced by a spirograph. In this simple mechanical model, we see the Sun orbiting the Earth in the center and Venus orbiting the Sun. Here we see the orbital track traced out by Venus in its geocentric orbit. Note that it passes from one boundary circle of Bhumandala to another. Here we see the same thing for Mercury. The alignment between the planetary orbit and the circular features of Bhumandala is approximate at 8 miles per yojana. If we choose about 8.5 miles per yojana, it becomes very accurate for all 5 traditional planets. Here we see the orbit of Mars. This orbital spiral also grazes an inner circle of Bhumandala and an outer circle. The Sun's geocentric orbit is a simple near-circular ellipse that runs down the center of one of the oceans of Bhumandala. It is noteworthy that the geocentric orbit of the Sun is so small compared with the Brahmanda that the Brahmanda is nearly Sun-centered or heliocentric. It is also worth noting that some commentators on the Bhagavatam take it to be fully heliocentric. The inner planets, Mercury, Venus, and Mars, are close neighbors of the Sun. For these planets, there is a 1-to-1 match between the 6 inner and outer boundary curves of their orbits and 6 bounding circles of Saptadweep, the inner system of 7 islands and oceans of Bhumandala. The Sun's orbit provides a 7th circle, dividing the 6 into 2 symmetric groups. The outer planets Jupiter and Saturn delineate a larger ring of Bhumandala lying outside Saptadweep. Jupiter defines the inner boundary of this ring, and Saturn nearly grazes its outer boundary, known as Loka Loka Mountain. As we mentioned before, this ring mountain is fixed in the Bhagavatam as the outer boundary of the luminaries, and Saturn is the outermost planet visible to the naked eye. Until recent times, astronomers generally underestimated the distance from the Earth to the Sun. Thus it is remarkable that the dimensions of Bhumandala in the Bhagavatam are consistent with modern data on the size of the Sun's orbit and the solar system as a whole. In particular, the Earth-Sun distance and the size of the solar system were seriously underestimated by Claudius Ptolemy, the greatest astronomer of classical antiquity. The detailed correlations between Bhumandala features and planetary orbits may seem contrary to the known history of science, but they are corroborated by historical data suggesting the existence of advanced scientific knowledge in the distant past. For example, a historical study of the yojana provides evidence supporting a yojana length of about 8.5 miles, the same length that emerges from the comparison of planetary orbits with Bhumandala. This yojana length is connected with accurate knowledge of the degree of latitude, and this requires accurate knowledge of the size and shape of the Earth. The historical evidence for the size of the yojana involves Greek and Chinese reports on distance measurements in India. It ties in with extensive evidence for the existence of scientifically defined measures in ancient Egypt and the Near East. And it is corroborated by the unit of measure called the hat that was used in the design of the 12th century temple of Angkor Wat in Cambodia. The orbital correlations are also supported by a statistical study reported in the text. Taking all of the evidence into account, the remarkable agreement between the solar system and the detailed structure of Bhumandala cannot be dismissed as a mere coincidence. Jambudvip is a topographical map of South-Central Asia. Jambudvip, the central hub of Bhumandala, can be understood as a local topographical map of part of South-Central Asia. This is the third of our 4 interpretations of Bhumandala. In the planisphere interpretation, Jambudvip represents the northern hemisphere of the Earth globe. However, the detailed geographic features of Jambudvip do not match the geography of the northern hemisphere. Consider this map of Jambudvip. The circle of Jambudvip is divided into 9 regions called varshas by 6 horizontal and 2 vertical mountain chains. The southernmost region is called Bharata Varsha. Careful study shows that this map corresponds to India plus adjoining areas of South-Central Asia. The first step in making this identification is to observe that the Bhagavatam assigns many rivers in India to Bharat Varsha, the southernmost division of Jambudvip. Thus Bharat Varsha represents India. The same can be said for many mountains in Bharat Varsha. In particular, the Bhagavatam places the Himalayas to the north of Bharat Varsha in Jambudvip. A detailed study of the Puranic accounts allows the other mountain ranges of Jambudvip to be identified with mountain ranges in the region north of India. Although this region includes some of the most desolate and mountainous country in the world, it was nonetheless important in ancient times. For example, the famous Silk Road passes through this region. The Pamir Mountains can be identified with Mount Meru in Ilavrita Varsha, the square region in the center of Jambudvip. Note that Mount Meru does not represent the polar axis in this interpretation. Cosmology and earthly geography. There are many cosmological traditions around the world which share important features of Bhagavata cosmology. These include a cosmic axial mountain or pillar, which is often identified with a local mountain, such as Mount Olympus in Greece. These traditions also include other standard features, including those shown in this generic world model. The cosmology of the Bhagavatam and the Puranas is shared in its broad features by Buddhism, and it is widespread in the Buddhist countries of Asia. This East Asian picture depicts a square version of Mount Meru and the oceans and islands of Bhumandala, surmounted by planetary orbits.